very basic configuration for BGP. We're going to set up a relationship between two routers as iBGP, so R1 to R2, and set up an iBGP neighborship, and then between R2 and R4 we're going to set up an Ebgp relationship. And the scenario here, just to get your head around things, is we're AS65001, and these are our routers, and we've just signed our contract with our new ISP, and that's their AS number 650002, and one of their routers. Now the rest of the topology is for later. What we'll do is we'll add to this tech video with further scenarios where we find that we want some fault tolerance, and then get another router from our into our network, and another one from the provider, and then we have so dual routes coming in here. Do a bit of load balancing, preferencing routes about which one we want first. We do conditional advertisements, we do non-exist maps, we do default route and originate, and we do route manipulation using things like origin and AS path length and all that good stuff. But for today we're just going to be discussing basic iBGP GP configuration, and we'll take it from there. So let's have a look what we've got already. I've configured R1's Fast Ethernet 0 interface, which connects to R2. Haven't configured R2 yet, so let's go ahead and do that. So in R2, we go in here, and let's just pop LAN address in here, and let's have a quick ping just to make sure that's come up. That's great. So that's R2 to R1. So let's configure the ISP link now. So normally when you go ahead and you get connectivity to an ISP, they'll give you a 30-bit mask, so that allows you to have two hosts plus the network plus the broadcast, and that's the way they conserve IP address registration. So we're going to follow the same sort of rules, because we should really, because it's just a demonstration, but we should try and keep that as close to reality as possible. So we'll have an IP address here, 24.111, and we'll give a 30-bit mask, 252. Let's just take that out. And R4, same there, 24.112. That's the only other IP address allowed in that 30-bit mask network. So 255. Whoops. 252, and we'll no shut that. Just wait for that to come up, and then we'll just do a ping of 24.111, which is our R2's interface connected to us, and great. So we've got comms there. That's super. Right. So let's go ahead and configure BGP. Now, what you'd normally do is you get this right first in your LAN, and then you do the connectivity to the internet, because obviously you don't really do anything crazy with BGP straight away. So let's just get the inside part working first. Okay, so just like a normal IGP, the keyword to configure BGP is router. Let's use the context help again, question mark, just to see what options we've got here. So we in our other tech videos we've used OSPF, we've used RIP, we've used the IGRP, and today we're going to be doing BGP. So there's the keyword. So router BGP. Let's see what comes next. And so we've got autonomous system number from 1 to 65,535. And so to get your AS number, you have to go to your local registrar. Here in Europe, we're in the UK, so we go to our local registrar, and they are RIPE. And the RIPE guys, you apply for your AS number and for your IP space, IPv4 or IPv6 space. And they allocate that number and those IP addresses to you, and they're unique to you. So that's the key with this autonomous system number. It's unique to you and your organization. So you need to go ahead and get that registered if you want to operate BGP on the internet. We obviously haven't got one because this is a demonstration today. So luckily there are some reserved autonomous system numbers from, if I remember rightly, 64.512 to 65.535. So we're not going to start at 64512 today. We're going to start at 65001. Only because that's the AS number most people choose, because it's easy to remember with the 001 on the end rather than 512. But anyway, it doesn't matter what you choose, as long as it's in the private AS number range. You're good to go. So root to BGP 65001. Hit return, and now we're in the subset of BGP configuration, and those are all the commands available to us. So all we're going to do today is configure an iBGP session with R2, who's our other router in our AS. So let's go ahead and do that. So the keyword we need is neighbor, and you see here we've got some choices now. So neighbor address, neighbor tag, and a neighbor IPv6 address. So we're only reading IPv4, so we're going to be using an IPv4 address. So we'll do neighbor, and remember router 2's IP address was 123.1.1.2. So neighbor 123.1.1.2, and these are all the options open to us, but we're just doing very lightweight, very easy iBGP configuration right now. So the only keyword we really need to configure is remote AS. So our local AS, if you remember, was 65001, and R2's still in our AS 65001. So R2's remote AS number is also 65001. Now the reason for that is we've got the same autonomous system number, and therefore we're under the same autonomous control. That's the whole reason for having autonomous system numbers. And by configuring the 65001 here in the remote AS, tells the iOS software that this is an iBGP scenario, because the remote neighbor has the same AS as me, therefore must be the same as me, therefore same autonomous system, therefore iBGP, internal BGP. So that's one side of the neighborship configured. Let's go to R2. We'll do the same thing here. Go to BGP 65001, and we've got neighbor 123.1.1.1 this time, because we're going from R2 to R1. Remote AS 65001 again. So here we've got our AS number 65001 and the neighbor's AS number 65001, therefore iBGP. So that's the neighbor configuration in. All we have to wait for now is the BGP relationship to be built. And if I'm quick enough, because I've totally forgotten, if we do a debug iBGP events and just wait around, as the BGP session is built, we'll be able to see that happen. There we go. So you'd see that statement anyway, but all this other stuff is all building. I'm waiting. I'm building sort of IPv4 BGP configuration stuff, debug stuff. On R2, you can see that the neighbor is up. Let's just run some show commands on here. So we've got show IPBGP summary, which is one of my preferred ones. So show IPBGP summary. This is just to give you a very quick output to show you what your neighborships are, what version you're running, AS number, that sort of thing. How many learned prefixes? See the PFX RCD. So on the internet now, you know, there are like 390,000 BGP routes out there. I can't think the last time I checked. But what if this was a router connected to something on the internet, and you were getting a full feed from a transit provider? You'd see this number here in that sort of 390,000 prefix sort of space. But we've got none. We're not learning any routes, and we can prove that just to do a show IP BGP. So if there were any routes in the table, in the BGP table, they would be in there. And if there were any routes in the routing table that were from BGP, they would be in there. And there's nothing, so no routes. Right, so let's configure the eBGP configuration, I beg your pardon, now between R2 and R4. So remember, R4 is our ISP. We're going to be trusting them to give us proper internet routes into R2. So let's go ahead and configure that relationship. So BGP 65000. Now if you remember, so this is our ISP, so that we're 65001, our ISP was 65002, different AS, different autonomous system under different autonomous control. therefore eBGP, external BGP. So router BGP 65002 and neighbor 24111 was us, remote AS 65001. So now we've got our autonomous system 65002, remote autonomous system 65001, different autonomous system numbers. And again on R2 to BGP 65001, which was our local AS number, neighbor 24112, remote AS 24111 65002. And again, we do the waiting game just to wait for it established now. If we'd done this when it was at this state, it would have said active there. So that means it's completed its handshakes and everything's done, and it's pushed over its topology table and all that good stuff. But again, we've got no routes here, so we're not sending out anything and we're not receiving anything. So let's just put some routes into this table, BGP 65002, and we'll just put one of these networks in right now. So remember, we configured a loopback interface here while we're waiting for the BGP topology to be built. This relationship to come up. So loopback is 0, IP address 150.111. That's just one of our loopback interfaces. Now to bring that into the BGP routing process, we use the network statement followed by the IP address and netmask of the network you want to bring in. Now, unlike an IGP, network doesn't mean activate BGP on this interface. So, for example, where you've got OSPF, if one of your Ethernet interfaces had IP address, say for example 1.1.1.1.1, 255.255.255.0, and you wanted to put OSPF on that network, you'd use the network 1111.0.0.0.0 area 0 keyword statement to enable OSPF on that interface. Well, on BGP, the network statement doesn't mean that; it just means push this network into the routing process. So we've done that with that statement there. So now, if we go to R2, we should be seeing some one route in the routing table from BGP. We do. So B is BGP. There's the network we introduced with the network statement. You see we've got a distance of 20 there. That is the eBGP default distance for iOS. And you can see we've been receiving that for 14 seconds. So from 24.112, which is R4's Ethernet interface closest to us. So there you go. So we've got the EGP session built and the iBGP session built. We've got one loopback interface on R4 injecting its network into the route process, and R2 picking up that route here in this routing table. And you can there's also show IP BGP, which shows you the BGP topology table, not the routing table. So this is like the RIB, the candidate for BGP to be able to push its routing table into the actual BGP routing table into the actual operational routing table. And you can see we've learned this network 151.1.0/24. So let's have a look at R1 here. Let's just get rid of some of this debug stuff. So let's see if we've got that network in our routing table. And we don't. So R4 has sent its network 151.1.0/24 into R2. R2's got it in its routing table. That's all nice. But R1 hasn't got that in its routing table. So what's the deal with that? Well, R2 will pass that route on to R1. So is it in R1's BGP RIB? Yes, it is. So here's the network, and we've learned it from 24.1.1.2, which is R4's Ethernet interface. And so here we go. Here's one of the principal challenges here with BGP. what we've got is we've got a network learned from our iBGP neighbor with the eBGP neighbor's IP address. Now, because R1 does not know how to get to the eBGP's IP address, it does not install that route into the routing table. So how do we get around this? Well, there are two ways off the bat that we can do here. One is tell R1 how to get to our 4's Ethernet interface. So remember, we've got the routing table just says nothing, right? Because we don't know how to get to 24.110/24. So we can either maybe configure OSPF between R1 and R2 and allow R2's 24.110 network into the OSPF process so that it advertises that to R1 and we learn it with OSPF. We could put a default route in, static route on R1 to point to R4's Ethernet interface, or we can use BGP to change the next hop IP address here to a next hop that the R1 will understand, which is basically its inside interface. So the network connection between R1 and R2 is 123.110. If we configure R2 to change the BGP next hop to an IP address 123.112, which is R2's inside interface, then this should all work. So we'll do that one first, and then I'll cover the we'll cover the routing table bit second. So in R2, we're going to configure mode again, configuration mode. Road BGP 001, that was our AS number. Now if you remember, we did the neighbor command again, so neighbor 123.111, that's R1's IP address, and we say next hop self. That's all we do. So now we're saying that when we're talking to neighbor 123.111, change anything that I give it from the next hop learned by me to my next hop, to my IP address, I beg your pardon. So it converts the next hop in the BGP information to me. So now where we have this show IP BGP showing the next hop is 24.112, we want it to say 123.112, which is R2's inside interface. So let's do that, show IP BGP. So now we've got 123.112. Now I know how to get to 123.112 because I'm locally connected to that network. Here we are, locally connected, 123.110. Yeah. So I know how to get to that network. So now, if you look, we have the old greater than sign there, and that means, I know how to get to that. I know how to get to that. So if we do a show IP route now, we should have the route installed in the routing table, which we do. And notice it's iBGP now, so the distance we've got is 200, whereas before the distance was 20. Oops. Okay, so that's changing the next hop so that we can have iBGP neighbors see routes which have the wrong next hop. They can't process that. Let's turn that off. So now we're going to go back to the bad old days where we can't use that route. Just have to wait for this to clear out. We can do a clear PPTP. That rips it out. Yeah. So you guys got it breezy. If you're in your lab, this is probably one of the most common ones when you get into the end of the lab, because it just basically resets the BGP process and makes it all start again. So there we go. So we've got the down and an up. Basically tore down the neighborship between router 1 and router 2. So now router 1's going to learn all the information it needs again. So we've got no route, but have we got it in the BGP table? Yes, we do. So here we are. We're back again. So the next hop is 24.112. And remember, we don't know how to get to 24.112, so we can't get there. So let's put in a route to 24.110. The net mask and the gateway. So the gateway is going to be R2's, the interface closest to us at R2, which is 123.112. So now we know how to get to 24.110. that mask, we should be able to get to 24.112. So this should come into the table without us changing the next hop now, right? So let's just have a quick look at that. Show IP BGP. What am I doing? So we know how to get to the next hop, 24.112. I think. What's your? There we go. Right. So it wasn't. It's very early in the morning here, but so network. You see, it wasn't in there. Now it is in there. So we know how to get to 24.112 now because of the static route we put in, and so now it's in the routing table. Let's just check that. See, it's in the routing table, and it is. So then you can see there's the full routing table. So you can see the static route we put in to get to the next hop, and we can see the route learned via that next hop there. Okay, so that's just two ways to do it. It's the other way maybe we could enable OS. So let's do the OSPF one. Let's take the just a little bit of fun. Let's take out the static route. So we've taken out the static route. So now the router does not know how to get to the next hop for that network in the BGP table. We do not know how to get to that next hop anymore. So this will age out as a valid route. Maybe. So you see what I mean about BGP, yeah? So if you're in your lab and you're running out of time, the last thing you want to do is wait for BGP to update itself. I mean, you can change the timers, but if the lab doesn't tell you to do that, you don't do that. So okay, let's leave that for a minute. Right, we're going to configure OSPF between R2 and between R2 and R1 to inject the network that R2 knows between R2 and R4 into the OSPF process, just so R1 gets into its table. So we're going to do this really quick because it's just an example. So router OSPF 1, that's our process ID, remember. That's locally specific to me. It's a process number, it's not an AS number. So we're going to do network. In fact, let's do this properly. So we'll do router ID 2.2.2.2 network 123.1.1.2. We'll give it a 32-bit mask, so it's just for that specific interface. We'll put that in area 0, and we'll do the same for network 1.0.0.0 area 0. So we configured OSPF and we're injecting the networks connected to closest to R1 and the network closest to R4. Okay, and then on R1, let's just check that's aged out now, which it hasn't. Great. Let's get rid of that. It's doing nothing. Let's get rid of that. So let's put OSPF on here. What am I doing? By the way, you don't have to do the router ID, but we'll use it later on in the example, so we might as well put it on now. Let's put the network statement in now. Reason we've got full with the BDR, so the other guy must be the DR. So hopefully the OSPF adjacency should come up. So we've got an OSPF tech video as well. You guys can have a look at that. So show IP OSPF neighbor. Let's have a look at this full. Yeah, so we're the DR. So R2 is the DR, R1 the BDR. Hopefully they're exchanging full routing table now, so let's have a look at that. Show OSPF database. Here's the OSPF database. These are the routes that I've learned, which is not a lot. I want to know the 24 one really, don't I? So let's get rid of all that debug information. Back to the story. So we had a static IP route before, and now we've got a OSPF learned route for 24.110/24 with the next hop of 123.1.1.2, which is R2's, locally connected, closest interface to us. And now low, there is the BGP route, again valid now because we can see a route to 24.1.1.2 via this OSPF LAN network here. So there you go. So we've done eBGP relationship here. We've done an iBGP relationship here. We found that the next hop needed to be connected. We need to be able to see the next hop, learn next hop. And when R4 injected its 150.1.1.0 network into R2, which was then advertised to R1, R1 was getting R4's IP address as the next hop. And because R1 doesn't know how to see R4's IP address, the route, even though it was in the BGP topology table, it wasn't in the IP routing table. So to fix that, we configured next hop self on R2 to change the next hop address provided by R4 into R2's IP address. And now R1 knows how to see R2 because they're connected on this LAN link here. So then the route was valid in the RIB table and therefore was allowed into the IP routing table. Then we took off the next hop cell from R2, so we were back to where we were. R1 was learning BGP routes from R4 with R4's next hop, and R1 doesn't know to see R4's next hop, so it wasn't allowed into the routing table. So to change that state, we put in a static route. So we put a static route from R1 so that it could see R4's interface here via R2, and then the next hop could be found, and then it was allowed into the routing table. And then again, just now we configured OSPF on R2 on the inside and outside interfaces to allow the network that's connected between R2 and R4 to be injected into the OSPF area here, which R1 learned. So once R1 had the OSPF network in between R2 and R4, it could then resolve the next hop, and then it could put it into the routing table. So there we go, just very basic stuff. Ebgp, iBGP, one route learned, and we took you through some next hop stuff. So join us next time for the continuation of this BGP tech video. Thank you for your attention.